Hello and welcome to this presentation on MATLAB to iPhone and Android made easy. My name is Bill Chow, and over the next 40 minutes or so, I'll be showing how you can take your MATLAB algorithm and run it on your iPhone or Android device. As you're working in MATLAB, you're writing scripts and functions to perform data analysis and visualizations, develop algorithms, and develop complete apps that include graphical user interfaces. So how do you take all of this and run it on your iPhone or Android device? So there's a couple of options for taking your algorithms down to your iPhone and Android devices. If you have Symlink, you can take a look at the target support packages that help you to take information from your sensors on board your iPhone and bring it into MATLAB. You can also take a look at using the target support packages for Samsung Galaxy so that you can take your algorithms in Symlink and put it onto a Samsung Galaxy device. So in today's presentation, we're going to take two things. So first of all, we're going to focus on algorithms that are written just in MATLAB, so there is no Symlink involved. And secondly, within your MATLAB algorithms, we're going to take just the numerical algorithm portion of your complete MATLAB algorithm, and we're going to generate readable and portable C code from it. And once we have the C source code, we'll integrate it into a new or existing iPhone or Android app running on Xcode or the Android Development Kit, which are integrated development environments provided by Apple and Google, respectively. And from there, the IDE will compile and download the app into your iPhone or Android device. And for this latter part of the process, we're going to assume that you have experience working on either iPhone or Android apps within the Xcode and Android Development Kit environments. One quick thing to note is that the code generated from MATLAB is going to be a part of the overall code base of your app running either on the iPhone or your Android device. So there's going to be a lot more other code that's running in the Xcode or Android project to make your app running correct, to make your app to run correctly on your devices. So in any case, let me show you the end result of an app running on my iPhone and Samsung Galaxy Tab 3. So switching over to my video feed, here you can see an app that's running on my iPhone. This is the geogravity demo that's provided by Apple. The teapot on the iPhone is balancing itself as I rotate the iPhone around. The app knows the direction of gravity using the data from the accelerometers. So as I tilt the iPhone, the teapot will turn as if it's resting flat against my desk. So I can tilt it up and down and in all sorts of different directions, and it's still doing its job well. So in this app, the data from the accelerometers is filtered by a simple low-pass filter before it's used to balance the teapot. So we can design our own filter in MATLAB and use it in place of the default low-pass filter. So over on my Mac, which you guys can't see right now, I'm going to actually go ahead and replace the low-pass filter with code that was generated from MATLAB. So in Xcode, it's finished compiling and it's loading the new app on my iPhone, as you can see here. And we've changed the low-pass filter such that, as you can see here, the teapot rotates much more slowly as I tilt the iPhone around. So this was done intentionally just so you can visually see that we've replaced the low-pass filter. And I'll show you a little bit more of how I did this towards the end of the day. So switching over to my other video feed, here you guys can see the Samsung Galaxy Tab 3, and within it we've got a custom app that's running right now. So what this app is doing is it's taking a video feed from the camera, and from there it's trying to detect all the corners that is in the image. So you guys can see all the corners, they're marked by pluses in the image, and there's actually three different corner detecting algorithms running, and that's why you can see the pluses in three different colors, either in green, blue, or red. There's also a couple of sliders you guys can see here, and this is adjusting the threshold all of the different corner detecting algorithms that's running. So I just lowered the threshold for the one of the algorithms, and in a moment here you guys can see there's a lot more red corners that's marked up in the image right now. So for the rest of the presentation, I'm going to break it down into two sections. In the first part, I'm going to show the basics of generating C code from your MATLAB algorithms using MATLAB Coder. So we're going to take a look at the challenges of manually translating MATLAB to C. But because of time constraints, we won't get into the recommended three-step workflow for automatically generating C code. But you can take a look at the MATLAB to C Made Easy webinar for more details. And in the second part, where we're going to spend the bulk of our time, we're going to dive into integrating the generated code into your iPhone or Android app. So to start off, you've got some MATLAB algorithm that you wanted to run on your iPhone or Android device. So with your existing process, it might look something like this. You have a MATLAB algorithm that you've tested and works well. So we'll call this V1. You or another person would manually rewrite the same algorithm in C, which we'll call V1 in C code. So you might have to iterate on the code to get V2 of the C code, which you guys can see here. And from here, you can get it to run on your iPhone and or Android device, and hopefully everything goes well there. So at this point, you might then go back to your V1 of your MATLAB code to incorporate some of the changes that you've made. So at that point, we're going to get V2 of your MATLAB code. So at some point, you're likely to get additional requirements or you're going to make changes to your algorithm. So then you have to iterate again in your MATLAB code in order to get version 3. And then finally, because you have this updated V3, you'll also have to update the C code with these changes. So with this approach, because these two languages are inherently different, there are many functional and behavioral differences introduced in your design. And the primary problem with this approach is that you have to maintain two separate implementations that are not automatically in sync with each other. So as we showed, if requirements change during development, it's quite inefficient to go back and modify the C code, then test it all over again to ensure that the functionality is the same as your original MATLAB algorithm. And coding errors are usually introduced during the manual translation process, leading to longer testing times and no guarantee that all bugs introduced are caught. And finally, this entire process, as I was describing it, is time-consuming and costly, as it's expensive to maintain not only separate algorithms in two different languages, but also separate test benches in C that actually may not get implemented, especially if you're on a tight deadline. So with automatic translation of your MATLAB algorithm to C, you spend much less time writing and debugging low-level C code and more time developing and tuning your algorithms. And so once you're happy with your MATLAB code, you start generating MEX files automatically, and you can bring it back into MATLAB to verify the compiled execution of your generated code. And so from there, you can generate source code and integrate it into your app. And of course, with this automatic code generation approach, you maintain one golden reference in MATLAB, and you can get to C code much faster. So having a single reference makes it much easier to make changes as the requirements change. And you also get to test it more systematically and thoroughly to account for more real-world scenarios. So let's now look at a simple demo that introduces the basics of MATLAB Coder. So I've got MATLAB here, and I'm going to start with a simple function. We'll call this myMult. And myMult is going to take two inputs. And all it's going to do is simply multiply two inputs together, A and B. I'll call this myMult. In addition, I'll create a very simple test bench, and all it's going to do is it's going to call myMult, and it's going to multiply two numbers together. I'll call this my test bench. Do that. So now if I call my test bench, it's going to then execute my mult, multiply two inputs together, and it's going to give me the output, which is 200. So at this point, let's say I'm satisfied with my very, very simple algorithm. And let's try to generate code for that. Come down here into my code generation section, and then I'll launch the MATLAB Coder app. So in here, this is the MATLAB Coder app, and the first thing we need to do is to specify the file that we want to generate code for. In this case, it's going to be my mult. So I'll input that, move to the next step. At this point, I can, in order to generate C code, I need to specify the input data types and sizes. Now I can do this manually. So if I click on that, I can come down and I can start typing stuff in here. Maybe this is a single precision, 1 by 1, or what have you. But actually, since I have that test bench, or just anything that executes the function I want to generate code for, I can use the auto-define feature. So if I click on this, what it does is MATLAB Coder will execute my test bench, and then from there it's going to infer the data types and sizes of my inputs. So in this case, it figured out both of these are double precision and they're just single elements. Then it's going to populate that, and so you can see that the auto-define feature is quite useful if you have a lot of inputs. So we'll take those and we'll go to the next step. As you go through code, you could introduce runtime issues as you're coding inside of MATLAB. So MATLAB Coder, we can go through and it'll do this check to see if there are any potential runtime issues that may result. And so we can go through. And so it went through it, generated the trial code, built the MEX file, and then it ran the test file with the MEX, and it figured out there are no runtime issues. So if that's good. We'll take that and we'll go to the next step. So from here, we can select which type of output we want. It can generate source code, MEX files, libraries, static and dynamic, and also executables. To keep it simple, I'll select source code and generate code from there. So code generation was successful. Our output, my mult.c, here's the generated code, and it's exactly what we expected it to be. Return a multiplied by b. Now we could do one other thing is, so our input, as you saw here, we had 2 single elements. But what if we started changing things around? So now let's make it multiply 2 sets of 2 matrices together. So I just changed that in my test bench. Now if I run it again, you'll see that our output is going to be a matrix of size 3 by 5 because our 2 inputs are 3 by 4 and 4 by 5. And that output matrix size is exactly what we expect it to be. So all we did was we changed my test bench. My mult hasn't been changed at all. And coming back into the app, let me go back into our second stage of defining input types. So I'm going to run the auto-define feature again and just watch the data types and sizes of our inputs. As we run it, you can see that it's been updated. So MATLAB Coder understands that in this particular case, we're inputting matrices of those 2 sizes, and so it updates the code generation settings for the input types automatically. So that's all we're going to do. We'll go to the next step, and we're not going to have any issues with that, actually, so I'm going to skip it. So now I'm going to come back and regenerate code. So we just finished generating code, and if you come down and take a look at my mult, you'll see that the generated code has changed. So now, in fact, we have 3 nested for loops that's going through, and it's doing all the matrix multiplications. So that's pretty straightforward, and as you can see, by updating the data type, input data types and sizes, we can change the generated code as we see fit. Now I'm going to do one more change here on the left. So in our output files, you can see there's actually a lot of supporting files. There's files that will support IFs, infinities, and not in numbers. So that's something that for our purposes, let's say we don't need them at all. So if we come into the speed category, we can turn off this support for non-finite numbers. So at that point, we can go ahead and regenerate code. And you can see on the left here, you'll see a lot of the supporting files has disappeared. And actually our generated code, our generated code has not changed, as you can see over here. Okay, so that was a simple demonstration of what MATLAB Coder can do. So let me go back to the PowerPoint presentation. So the algorithms that you create probably won't be as simple as the example that we just saw. So to successfully translate more complex and real-world algorithms, there is a recommended three-step workflow. So I'm not going to get into too much details. As I mentioned before, take a look at the MATLAB to C Made Easy webinar for more of these details. But I'll just mention quickly that with these three steps of preparing your algorithm, testing it, and generating, this is the recommended workflow, and this will save you a lot of time as you work on generating C code from your MATLAB algorithms. And as you go through the recommended three-step workflows, you should take a look and look at your implementation constraints. So if you look back at the simple algorithm I was just showing you, where we multiply by 2 inputs, that could mean a couple of different things. In the first case, it was the element by element multiplication. It could mean a dot product, or it could mean a matrix multiply. So what that means is, and the other thing is your data types could be real or complex, so that adds more complexity. So because of that, as you get to see this, from the same piece of MATLAB code, your generated C code could look as easy as return B multiplied by C to something that's a little bit more complicated with the matrix multiplication. And if you're looking a little bit further at implementation considerations, there's essentially 4 types that you need to be aware of. The first one is polymorphism, which is what we just showed. So that same piece of MATLAB code can be used to generate C code where it's multiplying element by element, or it's doing a matrix multiplication. Another consideration is thinking about memory allocation, whether your data is statically or dynamically allocated in memory. Then you also need to think about how you want to process your arrays. So MATLAB uses compact, optimized single-line expressions, whereas C code uses for loops. And there's also a difference in the zero-based indexing in C versus one-based indexing in MATLAB. And finally, you have to specify the data types in your input and output arguments, as well as the internal variables. So the effect of all these different implementation consideration means that 7 lines of MATLAB code for, say, a Kalman filter can turn into 107 lines of C code, depending on your implementation constraints. So breezing through this a little bit, if you look at the MATLAB language support, it follows that not everything in MATLAB would make sense for generating code in C. And remember, our goal is to focus on the numerical computation portion of your complete MATLAB algorithm. And so a subset of the MATLAB language is supported for code generation. The support is actually quite wide, as you can see here. In any case, this is the range or the subset that makes the most sense in converting to C code. So as a design engineer, you'd use many of these features that you can see here in your algorithm design. So the supported language features include all of the standard matrix operations, the various data types, and the different program control constructs like for loops, while loops, and switch case structures. And there's support for more than 1,300 MATLAB operators, functions, and system objects for applications like communications, computer vision, image processing, phased array, robotics, signal processing, and statistics and machine learning. Okay, so now having gone over kind of the basics of MATLAB Coder, let's move into the next part of our presentation, let's take a look at integrating the generated code into an iOS app. Okay, so switching over to my Mac, before we jump into Xcode, let's take a look at the low-pass filter that we're going to generate code for. So here's MATLAB again, and the file that the low-pass filter algorithm that we want to generate code for is inside of xyz_filter. And inside of here, you can see that we are using the system object from DSP Systems Toolbox, dsp.byquadFilter. And as we are designing the low-pass filter, we wanted to figure out what filter order and what cutoff frequency we wanted to use. So ahead of time, let's go to the cutoff frequency first. What we did was, from the iPhone, we got the required data from the accelerometers, and we loaded it into the Mac and then into MATLAB. So from there, we took a look at how we can smooth the accelerometer data coming out of the iPhone. So we're using the same set of data. Here on the left, this is one data set. The graph here at the top in red, this is the X coordinate data. In green is Y axis, and then blue represents the Z axis. For this data set here, we're using a Butterworth filter with a filter order of 2 and a cutoff frequency of 2.5. Same set of data on here on the right, but instead we changed the cutoff frequency to be 10 Hertz. Everything else is the same with a second order Butterworth filter. So looking at the responses of our outputs, which are the dotted lines here, you can see that immediately the jagged edges of the inputs are smoothed out by the Butterworth filter. And comparing these two sets of filtered outputs, one thing that jumps out is that there's a delay from the output of this filter here on the left. But the filter output on the right, while it is a smoother output, it's not as smooth as what we see here on the left. So for our purposes, we're going to go with the cutoff frequency of 2.5 Hertz with this particular set of parameters. So we've chosen the cutoff frequency. What about the filter order? So we did the same thing again. Same set of input data, but this time what we've changed was the filter order. So here on the left, we have a Butterworth filter, a second order Butterworth filter at cutoff frequency of 2.5. And the one on the right, we've changed the filter order to 8, but still kept it at the same cutoff frequency. So again, looking at the different outputs here, when the filter order is increased to 8, you guys can definitely see the delay in the outputs. And compared to the smoothness of the output, it's about the same for both sets of filter parameters. And so for our purposes, we'll go in the end with a second order Butterworth filter with a cutoff frequency of 2.5. So coming back to MATLAB, again, this is the code that we want to generate code for with the biquad filter. And so ahead of time, we create a MATLAB coder project that's going to generate code from XYZ filter. So click on Next. And ahead of time, I've actually predefined all the different parameters needed to generate code for that. We'll jump through. And actually, for runtime errors, you guys can build that. But for the sake of time, I'm going to skip over that. But it's always a good idea to run the runtime error check. I did it ahead of time. There were no issues. So finally, coming down here, let's go to this. We're going to generate code as source code. And then from there, we'll go ahead and generate code. All right, so everything is set. I'm going to close that over here. Here's xyzfilter.c. And you guys can take a look at that XYZ filter. The rest of this is a whole bunch of code that's going to represent our second order Butterworth filter. And this is in the form of a biquad filter. So that's the generated code here, XYZ_filter. and there's also our associated header file. So having done all that, I'm going to switch over to Xcode, and I will bring up a modified version of the GL Gravity demo. So rolling back out, GeoGravity, you guys can grab this from the Apple websites. And the changes I've made in here is, in this project, I created a new folder called MATLAB generated files. And the files that I generated over here in MATLAB, xyz_filter.c, the header file over here, filter types, RTW types. So what I did was I actually dragged all of those in here so that the Xcode project is able to see them. This is the same set. I'll bring that up. You guys can see that's the same XYZ filter that we were just looking at. Okay, closing that out. Oh, sorry. So let's take a look at GeoGravity app delegate. So in order to start using this low pass filter, we just have to change a couple different things. So in GeoGravity app delegate, this is kind of the top level file where we have to change things in order to call the low pass filter that we created. One thing we need to do is we need to add a pound include our xyz_filter.h. That's the header file. And then from there, we need to call the initialization. And within this application did finish launching, we added xyz_filter_initialize. Over here, I should have shown this to you. This is the header file for our generated code. And in here we have the main function xyz_filter. There's an initialization inside of xyz filter initialize, and also some termination in here. So there are three functions we need to call. So the first thing you need to do is call the initialization function within application did finish launching. Next, coming down in deallocate, make sure you add the xyz filter terminate function in case any resources need to be deallocated when the app closes. And finally, in your main function, which in this case in GeoGravity is the dig accelerate function. So originally what we had here was, this is actually the original code. So we had the demo itself came with a basic low pass filter, which you guys can see here. The inputs are acceleration, and it's broken down to the X, Y, and Z components. So if we wanted to go ahead and actually, you know what? Let me run this very quickly. Okay, so let me actually go ahead. I'm not going to use the generated low pass filter. I'll use the original, and I'll click on play. And this is going to compile and download it into my iPhone. And switching to my video feed, here's my iPhone, and we've got the original GeoGravity demo. As you can see, it's shifting orientation very, very fluidly because the low pass filter is not rejecting any sudden movements. So we can do this, and it's going to reorientate very, very well. So coming back to my Mac, so I'm going to stop the app. And now in order to use the generated code from MATLAB Coder, I'm going to comment those three parts out. And I'm going to call XYZ filter, and I'm going to feed in the X, Y, and Z components of the data from the accelerometers. So I'll click play. And switching over to the video feed, the app just compiled and it's downloaded and it's running on the iPhone. And now, as you can see, the low pass filter that we implemented, it rejects any sudden movements beyond 2.5 hertz. And so we can do really, really rapid jerks to the iPhone, and the accelerometer data, it's not going to pick that up. So you can see the teapot rotating much, much more slowly. So that's it. That's just a simple demo of running the low pass filter onto an app that's running on the iPhone. So wrapping up that demo, what you saw again was within MATLAB, using MATLAB Coder to generate C code, and then from there manually taking the generated C code and importing it into an Xcode project. And so from there, you can compile it down into your iPhone or iPad app, and you can deploy it and run it on your actual hardware. So I hope that demo and workflow showed you what it takes to take the generated code from MATLAB and put it onto your iPhone and iPad app. So coming back to the PC. Okay, so moving on, let's take a look at the final section of this webinar, and let's take a look at getting the generated code onto a Samsung Galaxy Tab 3 tablet. So to get your MATLAB algorithm onto an Android app, it's a little bit more involved. To illustrate that, I'm going to show this little diagram here. Working backwards from that, first of all, we want to take a look at the MATLAB algorithm, and then we're going to convert it into C using MATLAB Coder. So from here, with the generated C code, we need to then compile it into a .so file using the native development kit, the NDK, which is also provided by Google. This .so file can then be called from the Java app, which is our Android app, and of course we're programming this either through the Eclipse ADT plugin. Finally, this app is then called by the Android OS, and we can work with this using the SDK from Google. So we're kind of going to go through this process starting from the bottom. We're going to take the generated C code, compile into a .so file using the NDK. From there, we'll then put it into our Java app. So let's take a look at that. So first of all, I'm going to go into MATLAB, clean this out, and switch over to this. Okay, so I was showing earlier on the Android app, we have an algorithm or an app that's detecting the corners of a video image that's coming in. So I mentioned that there were 3 different corner detection algorithms running, and this is where it was implemented in MATLAB. We have the Harris corner detection. Actually, let me comment down. So we're using Vision.corner detector from the Computer Vision Systems toolbox, and we're using a couple of different methods from that. So let me come down here. So the 3 different corner detection algorithm. The first one is FAST, which you guys can see here, that algorithm. Coming down here, the second algorithm is the classical Harris corner detection algorithm. And the third one is the Shi and Tomasi minimum eigenvalue corners algorithm. And within our MATLAB algorithm, one thing that we're doing is we are setting the thresholds. So in the first case, that's F thresh, which you guys can see here. Second case, H for Harris, and the last case, M for minimum. So our inputs are going to be a video image in R, G, and B planes, and then we're also going to pass the 3 threshold values, which is part of the slider that I showed earlier. So this is a piece of code that we're going to generate code for, and ahead of time I've created a MATLAB Coder project in order to generate code from my corners, which is what we were taking a look at. So the input definitions have already been set, as you guys can see there. So we'll kind of breeze through this a little bit. No issues with runtime errors. And everything's been set up ahead of time, so we'll go ahead and just generate code. So we were able to generate code. Here's my corners.c, and I'm going to do a quick search. Corners. Here is the generated code, and you guys can see the 3 color planes, R, G, and B, coming in as the first 3 inputs into this function, and then followed by the 3 threshold values. Coming down here, you guys can take a look at a little bit more information. That's the Harris corner detector. That's the fast corner detector and the minimum eigenvalue detector. And we also have the associated header files, which you guys can see down here. And again, MATLAB Coder generated 3 functions. Here's the actual function to be called, myCorners, and then we have the initialize and terminate functions. So that's the generated code. One other thing I'll point out quickly, in this project, I've set the code to generate in a specific directory. And I'll show you what that means in just a little bit, but I'll bring that up. So the generate code is deposited into a specific directory, which is inside the Android project that I'm going to show you in just a little bit. So we'll get to that in just a moment. Okay, so we'll close that out, and we're going to switch over to the Android development environment. So here's here's Eclipse with ADT, the Android development tools. So right off the bat, here on the left, here's our project view, and in this case, we have 2 different projects. M Camera Slider, which is our main project, and the second one is OpenCV Library, which we're making use of. So the OpenCV library, this was downloaded from the web. This is the OpenCV library for Android, and we're just making use of that in our main function, our main project, M Camera Slider. And in order to make that work, we go into Properties. You guys can see here we're making use of the OpenCV library down here. Okay, so taking a look at M Camera Slider at the top level, let's take a look at layouts, or our main GUI here. The window's a little small, but here you guys can see here's the complete app, and with the app here we have a surface view, which is the view coming in from the camera, and so that's filling the bottom portion of this app. And at the top we have 3 sliders, which are going to be changing the value of the thresholds that I was talking about a little bit earlier. So the second thing to take a look at is the src directory. Our package here is com.example.mcameraslider, and within this is the one that we're going to take a closer look at. Here you guys can see our package, com example camera slider. Under import, we are using the OpenCV calls, and under camera slider and activity, let's come down a little bit. The main point to talk about here is we're calling and loading our OpenCV libraries, and as you get to this point in the code, that means our OpenCV library was loaded successfully. And from here, we're going to enable our camera. And then here's the important part, system.load_library. We're going to, this is the command that will load the .so file, so we can start using that. So all of that is within on Manager Connected. Now coming down, let's look for create. So coming down here in on create, here you can see we're loading our app menu, and this is called when the activity is first created. So we're going to load the GUI essentially, and from here we're going to start the background thread. Coming down a little bit in our background thread, we're going to go through. So we use the system.load library in order to load our .so file, but we haven't called our main function. And where we call the main function is in this background thread. and we're making a call of it into NA main over here. So if we look towards the declaration, this is going to bring us down. It is inside of main.c. So we're jumping to another file. Let me actually come back here. On the left, under the Java native interface, as I mentioned before, the JNI. These are files that we imported under SRC, and under corner down here, this is all the generated code that was generated by MATLAB Coder. And let me bring that back up. So under M camera slider, again, this mirrors the structure over here on the left, the JNI folder, SRC, and corner. So I specifically wanted MATLAB Coder to generate, or to deposit all the generated code in this directory. By doing so, the Android project will pick up the most recent version of my generated code, the mycorners.c and mycorners.h. So that's reflected inside of mycorners. And within our main function over here, this is the NA main that was called from over here. Down here. This is where it was instantiated. And within NA main, some initialization stuff towards the top. But again, mirroring what we saw in the iOS project, first we need to call the initialization function, and then you can deposit it, the actual output file, which is M camera slider. And then towards the end, we want to terminate that. So if we look inside of M camera slider output, this will bring us into another C file, mcameraslider.c. And coming down here, we'll be able to see that my corners is called down here through the update sliders, which is called over here. And one other thing too is actually through this update slider function, as the user slides their fingers on the three sliders, those values will then be updated over here. And so we're going to call my corners with R, G, and B, the three planes, the three color planes, and then we're going to enter the updated slider values over here, and that's going to call my corners. I think we can probably open that. Well, in any case, it's all within mycorners.c, which we were taking a look at earlier. So that's kind of the call tree, if you will, going through from the Android app, jumping all the way down to my corners. One part I haven't talked about is how the .so file is created. And that's actually created within android.mk. This is a makefile. This is something that you will need to create so that the makefile will then go through and create the .so file. So within here, we need to be able to call the opencv.mk because we're using OpenCV in our display drivers. We need to also bring in all the local SRC files that we need to compile. So here's the main one that we generate code for, corners, mycorners.c. In addition, we had that main.c file, which we took a look at, and also mCamera slider. And a couple of these other ones, these are drivers for the slider, the camera, and also the display. So from here, using this makefile, we'll create the .so file, which is then deposited into the library over here, lib mcameraslider.so. And that's how it will be able to go through and call my corners through the .so file within my Android app. Oh, one other thing I need to mention is in preferences, you also need to download and install the NDK. So once you download it, the NDK, you'll need to specify where the NDK lives. And you can do so here in the ADK preferences. So anyways, coming back up to the top level, so we got everything set up in the project, and from there we can go through and run this application. And we're going to run it on our Samsung. So we've got the app up and running, and here is the default screen. You guys can see all the different corners being identified with the pluses on the screen in blue, green, and also red. So we got the three sliders here as I was talking about, and we can start changing the thresholds of those different corner detecting algorithms, and we're going to see the screen light up with a whole bunch of red pluses, which are the corners being detected by the fast corner detecting algorithm. So I hope this demo and workflow demonstrates what you can do to take the generated code from MATLAB Coder, import it into an Android project, and then get that Android project downloaded onto your Android device so that you can start tinkering around with different algorithms and see how that reflects in the actual hardware. All right, so coming back into our presentation, wrapping things up. For more information, you can always visit the product pages. You can also contact your MathWorks account manager to request a trial license. With that, we can help you with a guided evaluation where one of our highly knowledgeable application engineers will guide you through the product and walk you through all the capabilities as it pertains to your specific application and needs.